Tonight's speaker, Brad Tucker, is an astrophysicist cosmologist. He is currently a research fellow at the Research School of Astronomy and Astrophysics, Mount Stromlo Observatory at the Australian Telescope, to understand why and how stars blow up. In addition to his research, he's also developed a series of astronomy coins in conjunction with the Australian Mint. He consults on science fiction movies, he's advised on astronomy-themed art projects, and he's currently working on a book right now, a science-related book. Tonight's topic, exploding stars, dark energy, and the end of the universe. Most giant stars end their lives in a brilliant explosion known as a supernova. The massive bursts briefly outshine all the light in their parent galaxy. The past 15 years have been a boom in research for supernova explosions, and they are important for the understanding of the life of stars, but they can also be used as cosmological probes to study what the universe is made of. And how the universe is accelerating and expanding is also the subject of a 2011 Nobel Prize with a gentleman he has worked with, and I'm sure he'll tell you about it. Tonight he will show how our understanding of these objects has revolutionized and what this means for the universe. So please join me in welcoming Brad Tucker.
Thank you, Lou. Just computer.
You want to do the sound test?
Sure. I have a loud enough voice, so I hope everyone can hear me.
Can you hear in the back?
Yeah. I'm the only one on TV who they have to turn down the mic for. Great. So thank you all for coming on this great Wednesday evening. Usually when it's anywhere, it's cloudy and rainy, so it's a bonus. So today I was going to talk about a little bit about what I'm doing, and it's aptly called Exploding Stars, Dark Energy, and the End of the Universe. Two themes you'll get at from this talk are we're doomed, and the universe is awesome, but it's going to doom us. So there will be a brief interlude where you won't actually be seeing what I'm showing you. You'll understand a little bit. Just don't tattle on me when we get to that point. And actually, some of the stuff, as I'll talk about later, which is the stuff you won't be seeing, is purely reliant on the Lick Observatory. And so if we don't actually have it, we won't be able to get the results we're talking about. So, a lot of the talk will focus on exploding stars, and that's because these are the tools to measure dark energy, and dark energy is what's going to end us. Well, the sun will end us too, and other things, but let's just ignore that for now. This will end us on a longer time scale. And exploding stars, called supernovae, are really cool. And it's a dark image. This is a M82, and it's called the Cigar Galaxy. And this star is actually an exploding star. And for reference, that's a star in our galaxy. So this object, which is 3 million light years away, is nearly as bright as that object, which is 12,000 light years away. And that's because these are very energetic things. They're equal to 100 million, billion, or Google says 100 bazillion lightning bolts. So imagine one lightning bolt, and then imagine 100 million, billion of them, all in one. That's what happens when a star blows up. Now you'd say, oh, these are really big explosions. They don't happen that often. Well, the one thing I can conclusively say we do know is these are actually really common occurrences. If you assume, and it's pretty well known, that each galaxy has roughly 100 billion stars. In astronomy, if you're off by 1 billion, it's okay. It's a great job to have. If every galaxy has about 100 billion stars, and we know there's roughly, again, about 175 billion galaxies in the universe, that means that every second, 50 stars blow up. So, already in the time of talking, I've killed thousands of stars. It's kind of a powerful tool to have. They're very common, so to speak. So which means is, if we want to use them to study anything in the universe, we have a good tool that is abundant, and it's out there. Now, the other great thing about it is, this is one of the few fields in astrophysics where the amateur astronomy community has a very big impact. A lot of the nearby important supernovas that we've ever found have been from amateur searches, not our professional searches. And in fact, this one, which we call 2014J, supernova are named by the year and then a letter of which it fell for, so that's the 10th supernova of 2014. And then you just get to telephone numbers, AG, blah, blah, blah. This was found by an amateur survey. So how do you say that a star that's 2 to 3 million light years away, relatively nearby, was missed by every professional telescope? That's because we weren't tuned for it. So if the amateur community did not find this one, which will go down as the most important supernova in history at this point, if they didn't find it, we would never know. And so it's actually a really cool community to have where the amateur astronomy community really helps out the professional community. Now, supernovae in their own right are really cool. Why? They allow a lot of different things to do with them. They're one of the few things in space when things take millions, if not billions of years, that actually happen in a few months. They'll blow up, you'll see them blow up, and then they'll fade. They happen on human time scales, and less than that, they happen on monthly time scales. It creates a very dynamic kind of universe. We think of the universe as this stale thing that just goes on, but really it's it's the happening place to be. They influence stellar evolution, how galaxies react. We can use them for studying the universe. We get to see all sorts of cool things like black holes and gamma ray bursts and everything you can think of that's cool. I don't think planets are cool, sorry. No, planets take away my money. No. Anything that's cool really has to go to supernova. Well, I guess a supernova can destroy a planet, so there you go. Now, let's take a step back. What are supernovae? So there's actually lots of different types. And we broadly call them by these various telephone numbers based on how their explosion looks. So if we measure how bright they get in blue, and we monitor how blue they are over time, you can see that they have different shapes. And as I'll say in a second, this is actually an outdated mode of talking about it, but astronomy likes to hold on to our nomenclature, so we stuck with it. And the real reason I like this plot is something this. So this is called 1987A. It was the closest supernova essentially in human history. It happened in the Large Magellanic Cloud, which is one of the neighboring galaxies that you can see with your own eyes in the southern hemisphere. And this is probably the most studied and well understood supernova that we've ever had. We have 10 to 20,000 supernovae now, and this is the most important one so far in terms of our understanding and how much time and resources we put in. And what do you notice? Doesn't fit any of our normal templates and classifications. So the one we know doesn't fit everything else. Now that obviously raises the flag. There's a lot to know. We could just say that's weird, but well, it's hard to say the thing you know about is wrong. So it shows there's a lot of stuff we have to do, but there's a lot of cool things that we get to study for it. Now, what do all these telephone numbers mean? Well, Fritz Zwicky in the 1920s and 30s started to find supernova, and some had hydrogen and some didn't. So if it didn't have hydrogen, he called it a type 1, because why not? And if it did have hydrogen, it was a type 2. But then he found some of the ones that didn't have hydrogen had silicon, so he called them a 1A, and they didn't. And further, there was helium, and there wasn't helium, and so on and so on and so on. And for tens of years into the 80s and 90s, this roughly held. But then we just started, things weren't quite what they seem. So when we actually look at these categories, when we look at the individual element, what's going on, you can see these blue shades. There's lots of iron in all of them. So supernovae are what produce iron in our universe. And yeah, this type 1A, it does have silicon, it does have sulfur and iron, it doesn't have hydrogen. Okay, fine. Now, this type 1B, it does have helium, this type 1C doesn't, sure. But then we started to find they actually did have hydrogen. And then we have type 2s which have hydrogen, but then we found that the hydrogen didn't go away. So the only thing we realized is that something was exploding. We really didn't know anything much else than that. So it's a really outdated mode that we still stick with. But eventually it's led to us to understanding that every group of supernova, the 1Bs, 1Cs, the type 2s, all of the ones that we think are different, are actually physically related, where these ones are the ones that are kind of weird. Now, there is something we do know, and that is how to find them, which is good, right? What you do is you observe, you look at a patch of the sky, and a few days later you go back, and you subtract the two, and sure enough, there was a supernova that went off in that galaxy. It's something that we can do a lot of. So what you do is you say, okay, well, here's an image. 4 days later, we went back and took this image. Can anyone see where the supernova is? So, there will be something in this image that is not in this image. Now you'll say, okay, well those three look different, and those two look different. That's not because, if anything, that's only due to the moon. So the moon got a little bit brighter, the weather was a little bit worse. So you have to take into those accounts. There's other things. So there's this spot here, there's that spot there and there. Those aren't real, those are cosmic rays. They're the, it's the junk of the universe, these high energy particles bombarding us. So you have to take all that into account. There is something new in this image that wasn't in this image. Who can find it?
Well, there's a dot in the lower right, up above there.
Nope, that's a cosmic ray.
Lower left.
Where?
Lower middle.
Cosmic ray.
Bottom left.
Bottom left? Here?
No, bottom.
There?
Nobody says there's something about
No. Any other, you got an idea?
Oh, yeah.
Confidence. Confidence is the key.
Key.
And if it's not right, you pretend it's right.
See, where's the on button? There's an extra dot.
Aha! Good eye. Well done. That is the supernova. You guys see that?
Yep.
Well, there's actually a second thing that's changed. So, luckily, we don't sift through millions of images. We have computers to do this now. So if you subtract the two, there's actually two things that have changed. There's, as you aptly pointed, that little dot, which wasn't there before, but mathematically, when you subtract these two, that in the middle is brighter than that one. And that's because there was a supermassive black hole that just ate a few stars. Now, that's great, but I don't care. You know, they're cool for their own right, but for what I want to do, I don't want to find them. So you have to, even when you find these, you have to go and follow up. Is it a real object? Is that what you're trying to do? So we know how to find them. We're pretty good at it. What else do we do now? We know that they're bright and they're long-lasting. So this is the movie, and this is what we call Supernova 12FR. So 2012 FR, so it was FR alphabetical if you want to go through all those combinations in 2012. And it exploded in October, late October, and the movie ends in January. So that. Those are all stars in our Milky Way. The galaxy is 13.6 million light years away. So when you play this movie right here...
Is that M101?
No, that's another one. That's 11FE.
Is it
All telephone
1365?
Huh?
Is it 1365?
This is NGC 1265. 1365, yes. That's right. So when you play this movie, out of nowhere, that blows up. So that, again, which is 12.5 million light years away, is brighter than these stars thousands of light years away. They're very bright, and it lasts a long time. So we know that. All right. Now, we do know some physical things about this. So I'll first talk about what we're calling the core collapse supernova. So those are those things that I call type 2s and 1Bs and 1Cs. And luckily, stellar evolution is something that actually works with us. So our understanding and belief of how stars evolve has told us that when you have a star and it's burning through its hydrogen and its helium, so our sun is currently burning hydrogen, and when it goes through that, it'll start burning helium. Well, if a star blows up at the point where it's still burning hydrogen, when you look at it, you'll see hydrogen and you'll see some helium. Great, we do see that. And if you evolve it a little bit long, you use up all its hydrogen and you start burning helium, what do you see? You see a star that's dominated by helium, but no hydrogen, a 1BC, or 1B. You evolve it a little bit more, and you get rid of that helium, and you start burning carbon and oxygen and nitrogen. You don't have hydrogen or helium. That's great, because we think we know that, and that's something we see. So naturally, we have to put them together. And when we look at the insides of stars, we do see that on the outside you get hydrogen, then you get helium and carbon and oxygen and so on. And when you get down to it, you get silicon. So then you would say, okay, the ones that had silicon but no hydrogen or helium or carbon must have burned all the way through and exploded at this stage. Okay, great. That starts to paint a picture. But how do these actually blow up? Now that's really where the cool thing happens. So as the star evolves, it starts to puff out its layers. So when our sun burns through its hydrogen, in order to puff out that, in order to keep it balanced, it starts to push that spent fuel away. So this is what we call a red giant star. So as our sun uses up its fuel, it will start to slowly expand. So the red giant, what is the sun, will grow and grow and grow, so it'll destroy Mercury and Venus and Earth. Mars may or may not survive, so if you want to buy land on some planet, go ahead and buy Mars. Yeah, it won't be hospitable for about 10 billion years, but sure, why not? The moon's not a good place to invest. As you puff out those layers, well, you still have this mass, it's just kind of like spent fuel, and you still have gravity pulling you in. So what has to happen? Well, the star has to burn more fuel in order to counteract the pressure of gravity, and then more and more and more. So you get this epic battle between pressure and gravity. And at some point, the star cannot sustain itself, and gravity pulls everything together and ignites the inside of the star, and then it blows up. So it's something we literally call a core collapse. The core, the inside of the star, collapses, everything comes crashing down, and it ignites in a big stellar bomb. So it's a really cool thing, and we wanted to put this to the test, and we were like, well, what's the best way to do it? Well, luckily, again, we had this supernova called 1987A. It went off, as I said, in the Large Magellanic Cloud, so one of these neighboring galaxies that we have, just very nearby. And the good thing about this galaxy is that we were able, beforehand, because people were studying the individual stars in this galaxy, to resolve the individual stars before the supernova. So in early January 1987, when someone realized there was something that just blew up, which is here, it was really bright. What we were able to do then is go back to the images that were taken before the explosion and see, was there a star located at the center? And sure enough, the object pointed to with an arrow is exactly at the center where that supernova took place. Now, supernovae do fade and they do eventually go away. So if you wait long enough, hopefully this light should fade, all the energy and explosion from the supernova should go away, and that star should disappear if it was the one that blew up in the way we thought it blew up. And sure enough, that star does not exist anymore. We've been able to image before the stars, see them blow up, and then confirm they disappeared. And what we found now is we're able to know that that is a 14 solar mass, so a star 14 times the mass of our sun, and something called a blue supergiant. So it's a large star in a certain evolutionary process. And the interesting thing about it was the first one we were able to do this technique with, this weirdo, if you remember from the earlier plots, that star was never theoretically predicted to blow up. All of our models said, oh, you can never blow up this type of star. It's impossible. That doesn't make sense. Sure enough, the first one we figure out was this.
What's the distance to that again? I forget.
The Large Magellanic Cloud?
Yeah. Roughly.
I think it's about 500,000 light years.
Oh.
Yeah, it's pretty nearby relatively, and so to speak. Again, 500,000 light years is close. Now,
How come they didn't think it would blow up? I mean, 14 is well in excess of 3.
it is, but it's a stage of evolution. So when you're what you call a blue supergiant, you're still actually a relatively young star. So when we look up in the night sky, blue stars are usually younger than red stars, and that's because the hotter you burn something, the color changes. So if you're hotter, that means you're still burning less fuel, and therefore you're younger. So we never thought a fairly young star could blow up. And this helped paint the picture that really changed that it doesn't matter where you are in your life, the bigger you are, the more you blow up. So it's kind of like celebrities almost. You know, it doesn't matter how long they are, where they are in their career, the bigger they are, the more likely they are to fall. Yeah?
160,000 light years.
There you go, even closer than I thought. Relatively close. See, Google. If you need to know something, and it can be looked up, you don't need to know it. Right? Hey, that's what physics is about. It's about applying things. And so that's right. It's one of the closest galaxies we have. But with the advent of the Hubble Space Telescope and our large telescopes like the 10-meter Kepler telescopes and the 8-meter Gemini telescopes, we've been able to do this on a lot more supernova now. So this is something called a 2008 CN. Again, this telephone number and it's a stock standard type 2, so one of these that we had just thought didn't have any hydrogen. And there's a supernova when it went off, and we went back. So on the top, we have before the supernova, and on the bottom, we have after the supernova. And sure enough, there's a star right at the center of the explosion, which has just been confirmed now that it's disappeared. A couple other different types, this thing, 09HD, another type of supernova. Again, there's a star right at the explosion of the supernova. And there's this one, a very nearby one, 2011 DH. It was caught very early. You can see here, there's nothing there, and there's something there. Again, we've had HST for this. Now, this one's a little bit slightly different, but it's the same argument. So here is the image before the supernova, and this is the image with the supernova. Okay? So here we have a fairly bright star, and here we've had, so this is 2013, so it's about a year and a half after that explosion happened. The light from the explosion is fainter than that star. So if that star didn't blow up, you wouldn't be able to see the supernova anymore because it'd be brighter than the old supernova explosion. So it's another way, even more creative way, of saying that star blew up. Because if it was there, we should see it there, but we can't. And if you actually add up all of this picture, this slide says as of now, but it's as of 2 years ago, and we've added about 10 more of these. You can see, so this is in terms of size of the sun. So this is 5 times the mass of the sun. This is 30 times the mass of our sun. You can see the range of supernova we get. Before we were able to do this technique, we always thought that supernova would explode between 5 and 10 times the mass of our sun, the lower limit. And of course, we're finding it's about 7 to 8. So perfectly within our prediction. So we can do something, right? And we can paint a picture now of how stars evolve and what they look like when they blow up, related to our telephone numbers. So our 2P is a red supergiant, our weirdos, just 87A is a blue supergiant, yellow supergiant, and there's a whole bunch of things. But then there's a category of things we know explode, but we haven't seen yet. So I said that this is pretty much most of the supernova we know about, minus this other type that I get to. But of course, now, as soon as you think you know something, you realize you don't know it. Again, science is one of the few jobs where you're paid to make sure you're wrong. That there's a whole new class of supernova. So here's the plot I showed before. So this is brightness. So those are all the ones I've talked about right here. That's how they fall in terms of brightness and how they long. This is the weirdo class that I was going to talk about. But then there's this new class. 10,000 times brighter than our brightest supernova we had. It came out of nowhere 5 years ago, and now we have 40 of them. And the great thing about this is we relatively think we know what these are. And these are the first generation of stars. So stars, just like families, are in generations. You had your first generation of stars that died, that gave birth to a second generation, that died and gave birth to a third generation. And the earlier generations were bigger than the later generations. That's because in the early universe you had mostly hydrogen and a little bit of helium. Well, it's easy to stick lots of hydrogen together, and so these stars are between 100 and 1,000 times the mass of our sun.
This is what they're calling the hypernova?
It was long believed this was a hypernova, but yeah, that's right. It's now superluminous supernova. But there was also a mixture related to gamma ray bursts on that too. So these are the first stars blowing up. So most of these live to only be about a couple million years old, relatively to most of these stars are between 5 and 10 billion years old. These happened between 200 and 500 million years ago, after the Big Bang, whereas these are 6 to 7 billion years after the Big Bang. These are really the first stars blowing up. And we've even predicted, based on models, that you can get a star that is 55,000 times the mass of our sun blowing up, which would put it about here. Or maybe even there. And telescopes like the James Webb Telescope, that apparently you guys are getting to talk about soon, are hopefully, that telescope will be among the first to find these. Now, if these are really what these are. So, now let's get to the cool ones, so to speak. And these are what I call the weirdos. And these are the ones that we use for cosmology. So, of course, it's very concerning when I say the weirdos are the ones we use for understanding the universe. And that's because it's something called a thermonuclear supernova. So the rest have been core collapse supernova, when the inside of the star collapses due to gravity and blows up. These, on the other hand, are very different. We know, and by know I mean at least 50% sure, so we know it, that it involves a white dwarf. And a white dwarf is an object which has gone through the evolutionary processes, so our sun will become a white dwarf in billions and billions of years. And it gets a neighbor next to it. Now, what the neighbor is really the seed of controversy. It's long been believed that you get something called a red giant. So let's take our solar system, for example, because there's a long-held belief that Jupiter is kind of a failed star. So let's say we get a star the size of Jupiter. Jupiter turned into a star. Well, it would evolve a lot slower than the sun because it's smaller, doesn't need to burn as much fuel, just like cars. So our sun would have turned into a white dwarf, and then later on, Jupiter would have turned into a red giant because that stage happens after a white dwarf. Well, if you get things that are close enough, the white dwarf still is pretty heavy and has lots of gravity. It can actually suck, kind of like a zombie almost, like sucking brains out or something, the outer edges of the star. So if you imagine our star, our sun, has hydrogen on the outside, well, if you had another heavy object next to it, it'd be pulling all of that hydrogen right off of it in this big stream of hydrogen. Well, Chandrasekhar in the 1920s said that once you get a white dwarf that reaches a critical mass of 1.4 times the mass of our sun, it automatically blows up because it's not a sustainable system. Well, we said, we know these systems exist. We know there's white dwarfs with red giants. We know this process happens. Well, if these are all happening, that means they're all blowing up at the same amount of mass. They're all blowing up at the same luminosity, the same energy, the same brightness. And therefore, these might be the standard candles I'll talk about, which is putting the picture together. But then someone said, all right, let's just have a backup plan in case that's not right. And that is, you just get a smaller star, so just a normal main sequence star like our sun, and the same process happens. And then there was a wild idea, wild at the time where no one believed, and now of course everyone believed it, because it's probably right, that instead of a normal star like this, or a red giant, you just have two white dwarfs, and they run into each other, and blow up. Now, as I'll talk about in a second, we have no idea what this is. We know how to use these things, which is always great, but we don't know what they are. Not knowing something has never stopped us in astronomy. What we do know about these things is that they all happen in the same process. They're not standard candles, they're standardizable candles. Okay? So, what do I mean by that? A star blows up, and it reaches a certain brightness. Well, naturally, it takes a while to get to that brightness and then fades. But if you have the same type of star, but is a little bit brighter, it takes a little bit longer to get to that top, to that maximum, to its peak brightness, and then a little bit longer to fade. Well, what was discovered in 1993 is there's an inherent relationship to how bright it gets and to how long it takes to get to that brightness and then fade. And if you correct for this trend and relate it to distance, you get this on the right. They all follow the exact same form. So if you can take out this relation between how bright they get and how wide they take, what we call the stretch, and you can relate that to distance, you can get something that has the same brightness all the time, and then therefore use it to do measurements in cosmology. So by doing this, we get something this. Velocity going out from us and brightness. They follow a perfect line. Now, what people did in the 1990s, so my boss, was the universe we thought was slowing down due to gravity. At some point it would stop and then collapse back on itself, called the Big Crunch. So if you have the Big Bang, you have the Big Crunch. Now, what they wanted to do is figure out how slow the universe was growing, when the universe was going to stop growing and collapse back on itself. What they found was the exact opposite. The universe is speeding up. So Big Bang's over here, we're over here now. The universe went like this, and is now speeding up. The universe is growing more today than it did yesterday. It's growing more tomorrow than it did today, and so on and so on and so on. The universe, its growth is speeding up. There must be something causing the universe to speed up, and therefore our universe will have the exact opposite end. It won't collapse back on itself, but will keep going out. Now this was a radical idea because, well, why would this happen? And multiple groups discovered it, and they won the 2011 Nobel Prize for it, the leaders of it. All of the teams got to go to it except me because I was getting married and I didn't get to go. I got an email message saying sorry. But this is something that was originally started on by Hubble in the 1930s. So Hubble, using a very different thing called Cepheid stars, so pulsating variable stars, so stars that puff out and in, and the more they puff, and the longer it takes, is also related to distance. So another cool thing, he found that, okay, the further out you are, the faster it is moving away from us. So the universe is expanding. And that's something we still call today Hubble's constant. The velocity, it's the speed of the universe. How fast is the universe going right now? But he never realized this because that is his plot retrospect to what we can do now. And that's actually kind of been zoomed in and enhanced because it doesn't really show up. So he never saw the universe was actually accelerating because he didn't have a big enough size to measure with. But now we can see that the universe is actually curving, it's actually growing. It's going like a roller coaster. Now, there's a lot to understand about why this is happening, and I'll touch on this in a bit. But what we need to do is figure out and improve the tools. Because I've said that all of the supernova can be related to this and follow this nice trend, get this nice measurement out. But I've lied. So, this is what a normal supernova should look like, this black line. But we started to notice, and we started to call these after specific types of supernovas. So 1991 T, so T supernova 1991, when you did this, it was really bright. Okay, that's an odd duck. Sure. Then there was another one just a few months later. It was too faint. Okay, fine, you have a weird one and you have another weird one. Well, unfortunately, if you were to take 1,000 supernova, 200 are these bright ones, and 300 are these faint ones. So already half are these odd ducks. Okay, well, sure, we just have some odd ducks, but we still have some good ducks. But regardless, we can still kind of do this relation that we talked about. So, okay, that's fine. Then we found another odd duck. So this is the faintness, so brighter supernova, fainter supernova. And this is that peak, so how long it lasts. Well, then we found a really bright one, but didn't take very long to get there. Okay, that's another odd duck. So we're at 3. But then we found one that was very faint, but took a long time to get there. So that doesn't work either. So now we're at 4 odd ducks. And unfortunately, these have 50 and 70 friends. So now we're at lots of odd ducks. And if you actually work it out, we have about 12 different types of these that we use for cosmology. Now, that's not very good, even by astronomy standards. But what we wanted to do is see if we can apply the same techniques to try and figure out what's going on with these stars as we did with these big stars. So this is 2011 FE, so this is the one I think you brought up. It happened in M101, fairly nearby. Really nice nearby galaxy. So the supernova, so if we zoom in on this galaxy, we zoom in even further, that little circle there should be the center of the supernova. So this is before the supernova went off, before the star exploded. If you draw a radius, where anything in that radius could potentially be the star that blows up, you don't see anything. The nearest star, these two, it's a 1 in 80 billion chance that those are the stars that blew up. It's even bad for astronomy standards. We know this technique of looking for the star before it blows up works. So why didn't it work for this one? Okay. Well, firstly, we believe that there's two stars that cause these things to happen. This white dwarf, this very massive, small object that our sun's going to turn into, and something else. Well, unfortunately, we're never going to see the white dwarf. It's too faint, it's too small. But we should be able to see what this other thing is, the thing that's having its stuff stuck off of. So if it's a red giant, it should be brighter than that middle circle. Nothing there. If it's a normal-sized star, a main sequence star like our sun, it should be just a little bit smaller than that circle. Nothing there. The only possibility that's left, it was another white dwarf. Because if you have two white dwarfs run into each other and blow up, you can't see either one of them, and you should never see anything there. Okay, so maybe there's just some white dwarfs that run together and blow up. Okay. Now, naturally you'd say, what's the problem with this? A white dwarf, so something to become a white dwarf takes between 10 and 12 billion years to evolve. So our sun's about, let's say, call it 5 billion years. It has another 5 billion years to go before it starts as a red giant phase. And then a few billion years even more to get to this white dwarf. It takes a very long time. Okay? Our universe is 13.8 billion years. How do you get two stars that take 13 to 14 billion years to both evolve and then blow up? And then how do you get stars that occurred 7 billion years ago that are 13 billion years old to blow up? And the universe is 13.8 billion years. We're missing about 6 billion years somewhere. So the problem is, while a few of these two white dwarfs should blow up as supernova, they cannot, for the life of us, understand how we get so many of them. It's a numbers problem. There can't be that many that are blowing up like this, and how much we're seeing. So let's start looking at a few others. So this is the one of the movie. It's just upside, well, mirrored. That's the supernova.
That's really pretty.
Using infrared imaging, so looking in redder colors than our eyes can see, with an 8-meter telescope in Chile, we imaged this area beforehand. And we were actually able to go deeper than Hubble, which was the previous image I showed. And we were actually able to conclusively say that it must be two white dwarfs, or two white dwarfs that are smaller than that. Okay, so we have two of these. Well, the odds are that two supernovae at random, just because they're nearby, that can do this, again, doesn't work statistically. It's about a 1 in a million chance. Which, okay, maybe in astronomy that's fine. But it makes us uncomfortable. Okay. Let's see, maybe there's another way we can do this. Let's scrap this technique altogether. In 2008, someone was looking at a galaxy at another supernova, 2007 something. And all of a sudden, so this is an X-ray, so this is the things that we use to image our bones. You can actually look at galaxies and see stars. All of a sudden, just for a few seconds, so this is in seconds, so that's 600 seconds, so 10 minutes, this big bump happens. Okay, well, what happened? There was actually, luckily, a supernova that went off while looking at the other supernova. Now, sometimes you have to be lucky. There's nothing wrong with being lucky. Luck leads to Nobel Prizes. Now, okay, what's this bump? Okay, it's a real supernova. So luckily, they caught onto it early. They were looking at the data in real time, so they triggered all of our normal telescopes to find it. Something interesting happened. This is something we call a shock breakout. So when a star explodes, you can actually see the shock wave before the star explodes. So imagine for a second a nuclear bomb. It's not really the best example, but it works. When a nuclear bomb goes off, you get the shock wave go through, and then you get the nasty bits after. When a star blows up, and you get everything collapsing down, you can actually see the ignite of the core go through the star, and then the star explode. Now, this only lasts on a scale of minutes to hours, which means you have to be lucky, or you have to plan it well. And how you plan to predict where a supernova goes off and observe it a minute after, that's hard to do. And what they found with the supernova is that, so this is the normal light curve. So this is 14 days after it blew up. So the peak should be about here. Less than a day, it's actually as bright as the peak. They were actually able to see the shock wave go through the star and then the star explode by being lucky. Now the cool thing about this, at least with this one, we call 11DH, is one that we had this Hubble imaging of pre. And our models of what the star is, so you can actually model this type of star that blows up based on how big the shock wave was, matches exactly what we saw from the Hubble Space Telescope pre-imaging and our conclusions. So we have two techniques that give the exact same answer, which never happens in astronomy. So that's cool. We have another technique that we're confident of. So this has only been done for these core collapse, these bigger stars. Let's see about type 1a supernova, these weirdos, these cosmology ones. So, we can apply the same thing. We have a star that blows up, so this yellow stuff's a star. Now, if we have another star here, and we have an explosion here, as the explosion comes, it's going to hit this other star. Two things will happen when it hits this other star. You'll get a hole, because the star is blocking some of this energy, but it'll build up in kind of a pressure, and then come zooming around, and shoot the star off. Now, the great thing about this is no matter where you are, you should be able to see it. So, I'm here, I'm on Earth, I have a supernova that blows up, and we have a star that was being sucked from it in front of it. So the shock wave happens, you get a hole, and you can get everything zooming around. What you actually see, if everything goes right, if you're looking down at it, you see this huge peak, and then you get this normal looking explosion here. But even if it's reversed, so the star's here, the donor star, so the one being sucked from is over here, you'll see just a little bit of it. But that's okay. If you have all these different views, if you have hundreds or thousands of supernovas, you'll be able to find these features. So it's using the same exact physics, the same exact understanding as we had from other techniques, which we now have two different ways to verify it, on this. And if you look at it, the great thing about it is this little bump early times, this shock wave, is inherently related to the type of star that it gets hit. So the bigger the star, the bigger the surface area, the bigger the bump. So with the red giant, the bigger stars, you get a really big bump. With stars like the sun, you get a small one, but there's still something there. So, I said at the beginning we had thousands of supernovae, which means we have thousands of supernovae to look at this. If we take all the supernovae we have, so there's about 1,200 in this plot, and we look at it, and we look at different colors, ultraviolet, blue, violet, red, even infrared, there's no bump. So remember, so you can match exactly this plot, should exactly match this plot. So that's 15 days. So 15 days. Where's the bump? So 1,000 supernova don't show this. Now, we have another problem. So, okay, we could say, all right, we can conclusively rule out that any red giant and white dwarf scenario blew up as this type of supernova, which has its reasons. Okay, so there's one, let's be negative Nancy here for a second. When we see a normal supernova, we catch it usually a few days after. So, all right, well, you can see there's a lot less points here than here, and so on. maybe we just haven't been lucky enough. Maybe we just haven't done it enough. So I've developed another program to do this. So the Kepler Space Telescope, who's heard of Kepler? The planetary finding one, it's done lots of cool things finding planets around other stars. Well, it's kind of in a broken phase. 2 of its things that make it point have recently broken. And we've come up with a new mission. So now, half the time, Kepler will not be looking for planets. It will be looking for exploding stars. And so the project I'm running on Kepler. Now you ask, why would you want a telescope that looks for planets to look for exploding stars? Well, the great thing about Kepler is it stares at the same patch of sky, and even though it's monitoring stars, there's galaxies where those stars are, and it's monitoring it every 30 minutes. Okay? So, these features, obviously, are biggest no matter what on the scale of hours. Okay? Well, with Kepler, we know that if a star blows up, when Kepler is viewing it, we'll see it at least 30 minutes after it exploded. So that one lucky one, that we got lucky on the other type, if we're monitoring it with Kepler, we should be able to see 100 of those lucky ones. So we did this. We did this with Kepler.